Today's lesson is again about waiting line analysis, and today we'll talk primarily about multi-server waiting lines. And like before, we'll go through an example to show you how things fit together. The thing that you'll find interesting again is that we're only going to change one small thing about what we saw from last time, and you're going to see how much more complicated the equations become. And then we'll give you a solution for that, on how to having to do all those calculations by hand. So let's dive in. And first is a reminder about what we did last time. We had a single server queuing system where we had one server, and our customers entered the system at rate of lambda. The distribution, probability distribution, was exponential, the time between arrivals, and then customers departed our system at rate mu, and again the service times also had the exponential distribution. And again, the key thing for this is one server. The queue is infinite in length. There's no limit. Once a customer enters in line, they stay in line, and they're served first come, first served. I left you with a problem last time with the Peachtree Airport problem. The question was, what's the chance that at least two airplanes will be circling the airport? And so again, the caution at the beginning was, if there's two airplanes circling, you need to translate that into how many are in the airport system. And it turns out, of course, if two were circling, then three were in the system. And then the other keywords were at least two airplanes in the system, which would mean three or more in the system. And so we wanted to find the probability that there were three in the system, 4, 5, 6, all the way out to an infinite number of planes in the system. And we said we know by the properties of probability that a lot of additions, an infinite number of additions, but the way to calculate that was to recognize that that's the probability of 1 minus these three conditions leaves everything else. And using the formula for P sub n for each one of these cases, that answer turns out to be 0.2964. Hopefully you were, with these input values, one server, arrival rate of 5, service rate of 7.5 aircraft per hour, and hopefully you got this solution. Or if not, we'll try that and make sure you understand how to get that solution. Next, we're going to talk about and review the elements of the waiting line. We said last time, for our purposes, calling population, or the number of customers that could enter the system, is infinite. It's unlimited. We knew we needed to develop and define an arrival process with an arrival rate of lambda and the exponential distribution. Again, service rate is mu with the exponential distribution. The service discipline, first come, first served. The queue capacity is also infinite. And in this case, the servers that we're going to use is going to be the case where S, the number of servers, is greater than, this is not equal to, the number of servers in today's lesson is strictly going to be greater than 1. And then how many service processes are completed? There's only going to be one service that's going to be completed. So it's very simple system, but very practical systems. So last lesson, again, this was what we studied. There's one server, one line, or one queue. And in this, what we're doing in today's lesson, there's still only one line. But in this today's system, that there are multiple servers. Now, the assumption is that each one of these has the same service rate. So they're homogeneous in terms of their service rates. But there's the key thing, and where students get confused. This is the situation where there is exactly one waiting line. This is the case that's similar to a bank teller. Actually, some grocery stores, some department stores, for example, if you go into Dick's operates like this. They have multiple servers, but there's only one waiting line. And the person, the customer who's next in line, who is this person right here, will go to whichever server is next available. Does not wait for a particular server, but has to go to the next one that's open. And in this case, server 3, the service is just finished. So this next customer goes to server number 3. That's the only change, is that we've gone from a single server situation to multiple servers, but they all have the same service rate. Again, the arrival process still has the rate lambda with exponential distribution. The service rate is mu, also exponential distribution. Customers, they always stay in line as before. The queue has infinite length, no limit to the line. There's only one line. That is one of the key things. There's only one line, and they're served to go to the next available server, first come, first served. So that's the only change is the fact that we have multiple servers. Again, our operating characteristics are going to be the same, although how we compute them is very, very different. So we'll still have operating characteristics related to the number that are either in the system or in the line. We'll have the waiting times that their customers are in the system or in the line only, or we'll be able to capture probabilities of how busy is the server, or what's the likelihood that a given number of customers are in the system. Now notice again, this is in the system, not in the line, which gets again a little bit more complicated when we have multiple servers. If you remember the last case with the airport, we had only one server. So if we said there were 2 in the line, that meant 3 were in the system. Now in this case, if there's let's hypothetically, let's say that we have we have 3 servers, and we wanted to know what's the probability that 2 were in the line. Well, that would mean that actually we would need to calculate P sub 5, because if 2 are waiting, there's also 3 that are serving. And so P5 represents the probability that there are 5 in the system, which is the same as saying that there's three servers and 2 that are in line. Just think about this. If there couldn't be the situation where there was a customer with 1 server, a customer with 2 servers, and then 2 in line. This situation would never occur, because here's our server 1, here's our server 2, here's our server 3. This would never occur because instantaneously, in terms of our model, this customer goes to server 3, goes to whichever is open. So this is the case where there's 3 that are being served. 1, 2, 3. And there's only 1 in our waiting line at that point. Okay, hopefully that makes sense. All right, at this point, let's look at, we're going to pause and we're going to continue up and pick up in another video. And we're going to look at another example. It's the Draper Clinic example, problem 5.10 on page 218 of your textbook. So let's pause and we'll pick up the video, pick up the lesson with the next video.